So, good evening students. Today we will see the next topic, which is heat transfer correlations for flow over flat plate, and also the next one is heat transfer correlations for flow through the cylinders or pipes. Okay, so first we will see the heat transfer correlations for flow over the flat plate. Suppose if anything mentioned like flow over anything, then that type of in heat transfer there are two types of flow. When there is a flow of air or when there is a flow of liquid over any object, then that type of flow is called as external flow. When there is a flow over any object, then that type of flow is external flow. When there is a flow inside any tube or cylinder, when there is a water is flowing inside the tube, or when there is a flow of air inside the cylindrical object, then that type of flow is which is flowing inside the tube. That's why that type of flow is internal flow. So first we are dealing with the external flow because this is heat transfer correlations for flow over a flat plate. Okay, so let us take this example. In this I am taking one plate. Okay, let us consider this as one plate in which the flow is air is flowing or any liquid is flowing over this plate. So this is air, this is plate. So air is flowing over this plate. When the air will flow over this plate, then what are the correlations that we have to understand and we have to study? That is this topic. Okay, not only air, any type of fluid or liquid you can take which is flowing over the plate. Okay, so as we have already studied, so when there are two mediums, one is a fluid and another one is a solid, then what type of or what mode of heat transfer will come and take place? Convection mode of heat transfer will come and take place. And in the first video I have also shared in the modes of heat transfer, convection we have studied. For convection, one governing law we have studied. What is the governing law for convection? We have studied that Newton's law of cooling, that is Q equal to H into A into delta T. This is the Newton's law of cooling, where what is meant by H? Heat transfer coefficient. Okay, so this H is main important thing in the convection. Okay, so this H will vary with respect to Q. How much heat transfer is there, then based upon that the H value will vary. So how can you write that H? May I write H is equal to Q by A into delta T, right? So this is the heat transfer coefficient equation, which is equal to Q by A into delta T. So this H is directly proportional to the heat transfer. There is a high heat transfer, then there should be some high heat transfer coefficient to take the heat away from the particular object. Okay, so there is a air which is flowing over there. For example, this point I want to know what is the heat transfer coefficient. So let us take, this is, I will give some colors. This is x-axis, okay, and this is y-axis. Okay, so at this point I want the H value. What is the H value? And suppose at this point I want the H value. Suppose at this point I want the H value. These are all Hx, means a local point. Okay, so suppose the total length of the plate is 3 meter. Okay, for example, for better understanding, for example, the total length of the plate is 3 meter. I want to know the heat transfer. What is heat transfer coefficient? Which is nothing but it is just extracting the heat, okay, per meter squared area, okay, to increase the to give the temperature difference of 1 Kelvin. Okay, that is heat transfer coefficient. So I want to know the heat transfer coefficient. Suppose at 1 meter distance, what is the heat transfer coefficient? How it will vary? That is depends on how much amount of heat is getting transferred. Okay, so it will vary with respect to Q and also the area. Okay, so the heat transfer coefficient will be different at different locations in the plane. Suppose I am considering only one dimensional, so the heat transfer coefficient value will be vary. At this point there will be one heat transfer, and this point there will be one heat transfer coefficient. So that some scientists, they have done so many experiments, okay, and they have framed one equation. That are the things that we are going to see in this topic, okay. So after identifying these things, they have done some experiments and then they found this equation, okay. So what we have studied already in the dimensionless parameters, one important dimensionless number we have seen. If you see the previous session of mine, you can also see that one topic I have taken in the dimensionless number, which is Nusselt number, okay. So Nusselt number is the ratio of conductance to the convectance, okay, convective heat transfer to the conductive heat transfer. So now here you see the same formula I have written, H into L by K, where the numerator is convective heat transfer and denominator is the conductive heat transfer, okay. So to find out the local Nusselt number, first to find out the heat transfer coefficient, these formulas and you all please remember while solving some numericals in your examination. Suppose sometimes they will ask directly find out the Nusselt number, okay. Nusselt number formula is this one only, Hx into L by K, or simply you can say H into L by K. Suppose if the flow is taking place over the plate, then this formula you have to consider, Hx into L by K, okay. Now to find out the Hx, we need the Nusselt number. So without knowing this, you cannot find out the H value. So this formula, you don't worry, this is very big in so that you no need to remember this formula and all. They will give in the question paper Nusselt number equation this much only, 0.332, Reynolds number power 0.5, Prandtl number power 0.333. So that you should know the meaning and formula for all the dimensionless numbers in heat transfer always. Okay, so what is the meaning for Reynolds number? What is the definition for Reynolds number? What is the formula for Reynolds number? Okay, suppose Reynolds number, if there is a plate, then rho v L by mu. Okay, if there is a tube or cylinder, then rho v D by mu. Okay, then what is the Prandtl number, which is the ratio between the momentum diffusivity to the thermal diffusivity, okay, which is mu Cp by K. That also you should remember. Okay, sometimes they will ask you to find out the Prandtl number alone. I have seen some of the questions in the GATE examination. In that examination and ESE also, they have simply asked to find out the Prandtl number only. So what is the formula for Prandtl number? Mu into Cp by K, where what is mu, which is the viscosity, Cp, you know, that specific heat of the particular liquid or any kind of object, then K is the thermal conductivity. Here we are talking about convection, so only air or liquid thermal conductivity we have to take in the Prandtl number. Then similarly we have to find out the Nusselt number also. So these are the correlations that we need to understand when the flow is taking place over the flat plate. Okay, so this is the first question, the local Nusselt number we have to find out. So why we need to find out the local Nusselt number? Because I want this heat transfer coefficient at this point. Suppose the total length is 3 meter, I want the heat transfer coefficient that is 1 meter from the, so this is leading edge as we already discussed in the boundary layer concept. This is leading edge, this is trailing edge. Okay, suppose I want to know that heat transfer coefficient value, okay, 1 meter from the leading edge, then you have to find out the local heat transfer coefficient. Local heat transfer coefficient, that is Hx, is available in this formula, so that Hx into L by K. So you have to find out this equation. Okay, next one is, after finding out, suppose you want to know the average heat transfer coefficient, there is one simple derivation for this, so that we no need to study. We just remember the formula. If the flow is taking place over the flat plate, then average heat transfer coefficient equal to 2 times of the local heat transfer coefficient. That is H is equal to 2 into Hx. That you just remember, that's all. Okay. Then hydrodynamic boundary layer thickness or velocity boundary layer thickness. This topic is not available in your syllabus. Thermal boundary layer only they have given. So just you see this formula, delta Hx equal to 5x into Reynolds number power minus 0.5. Sometimes they will ask this also in some numerical problem. Just we need to find out only the hydrodynamic boundary layer thickness. Okay. What is a hydrodynamic or velocity boundary layer thickness? Means same thing as we have discussed here. So here when the flow is taking place, what will happen? So the layer, what is the boundary layer? The layer which is adjacent to the plate, which is called as the boundary layer. Okay. Now suppose if the flow is the liquid is flowing over this plate, okay, what will happen? The layer which is adjacent to the plate will have the zero velocity because it has no slip condition and it will be sticking on the surface of the plate, then it will be at the same velocity of plate. Then when we go just little bit up, that adjacent layer of the first layer, if you go in the upside, then you can see the fluid layers will have some velocity. Okay, likewise the velocity will grow up. That is velocity boundary layer. How the velocity boundary layer is forming? Okay, like this it will form. Okay, so like this. So here it will be 0, then the velocity will gradually increase like this, then at last it will reach the free stream velocity which is flowing over the plate. Initially it will be 0, means on the surface of the plate it will be 0, then finally gradually its velocity will increase when it is moving upside, when you go in the upside direction, then at last after some time it will reach almost 99% of free stream velocity. After that the velocity of the fluid or liquid will not change. So that is, so up to that distance the layer is forming, so that up to that distance if you take, then that height is velocity boundary layer, that is delta Hx. Same we have seen thermal boundary layer, this is also velocity boundary layer which is 5 into Reynolds x into Reynolds number power minus 0.5. This value and all they will give. X means the distance, at what distance it is. Next one is thermal boundary layer thickness, as we have already studied. For flat plate, this is important. Sometimes cylinders also it will be there, but this is for flat plate, which is delta Tx equal to delta Hx into Prandtl number power minus 0.333. This formula sometimes we have to remember. In question paper they will simply ask to find out the thermal boundary layer thickness by giving these all values. They will give the, this is hydrodynamic boundary layer thickness, and they will give the Prandtl number also. They will simply ask us to find out the thermal boundary layer thickness. So that time we have to remember, at least you just remember this formula, what is thermal boundary layer thickness. Okay, and thermal boundary layer thickness is always having the link with the Prandtl number. While we solving the numericals, I will explain you clearly how this Prandtl number is related to thermal boundary layer thickness, and it is also having link with hydrodynamic boundary layer thickness also. So Prandtl number is one of the important dimensionless numbers which is also giving link to both velocity boundary layer and also thermal boundary layer, that we will discuss later. Next one, local friction coefficient. Friction coefficient in the sense when the fluid is moving, then there will be some friction between the fluid layer and the surface of the solid. So that friction coefficient is there, that is Cfx for flat plate 0.664 Reynolds number per minus 0.5. You just see only the formula, no need to muck up. That kind of thing they will give in the question. Okay, I just want to say you these things are there to know their correlations of heat transfer in the flow over flat plate. Next one, average friction coefficient, which is CFL bar equal to 1.328 into Reynolds number power minus 0.5. Okay, next one. Next topic, for flat plate, that thing I forgot that. This one is for the condition is laminar flow. If the flow is laminar, what is a laminar? What is the condition for laminar? If the, how will you find out whether the flow is laminar flow or turbulent flow? What is the significance of the Reynolds number, which is used to find out the type of flow, whether the flow is laminar or turbulent? What is the Reynolds number value for laminar flow? If the Reynolds number value is less than 5 into 10 to the power of 5, then the flow is laminar flow. So that first you have to find out, the first step in solving the numericals, heat transfer problems, okay, in convection, you have to find out first whether the flow is laminar or turbulent. So that you have to find out the Reynolds number. Then if the flow is laminar, then these are the formulas are there and these are the correlations are there. Then suppose if the flow is turbulent, then the formula will change. So as we have seen for Nusselt number, local Nusselt number, laminar flow, that formula same, but this value only changing. 0.0296 into Reynolds number power 0.8 into Prandtl number power 0.333. I am sure that I am giving you assurance this formula and all we no need to muck up. Okay, they will give in the question, no problem. They will just give and ask us to find out the heat transfer coefficient only. Okay, so this Nusselt number formula always you should remember Hx into L by K. After finding out that we can find out this Hx. You all will understand while we solving the numerical problem. Okay, after solving completion of this I will solve one numerical problem. Based on this then you will understand why we are studying this topic. Then how to solve the problem on this topic also you will get idea after solving some numericals on this. Okay, average heat transfer coefficient for the turbulent flow. For laminar flow average heat transfer coefficient is 2 times of local heat transfer coefficient, but for turbulent this is important. For turbulent 1.25 times of local heat transfer coefficient. Okay, next one is boundary layer thickness. For this case there is only boundary layer thickness, there is no velocity and thermal boundary layer thickness. This is the formula 0.37 into x into Reynolds number power minus 1 by 2. Okay, this formula also you please remember, sometime it will be useful to solve some problems. And local friction coefficient Cfx is equal to 0.0. All formulas you just note down, if you want you just remember. Cfx is equal to 0.0576 into Reynolds number power minus 1 by 2. Only I am just writing the formulas, we no need to go in deep about these things and all. Okay. Then flow through pipes or cylinder, that is called as internal flow. So that I have already discussed in the beginning of the video itself. When there is a flow which is flowing inside the tube or cylinder, then that is internal flow. Then if the flow is laminar, then Reynolds number should be less than 2000. Okay, then for the, this is important, in some of the examination they are asking only these values. What is the Nusselt number? When this you please note down and don't forget also what is the Nusselt number flow value for the flow through pipes if the case is laminar flow. Suppose if there is a pipe, okay, inside the pipe liquid is flowing, if you apply some constant heat flux on the wall of the tube, then the Nusselt number is 4.36. Same tube, instead of constant heat flux, if you apply some constant temperature, instead of this, if you apply some, suppose if you maintain the temperature of the wall at constant temperature, you are maintaining the wall temperature is constant, then that case Nusselt number is equal to 3.66. There are two conditions. One is maintaining constant heat flux of the wall, another one is constant temperature of the wall. If you maintain constant heat flux for laminar flow, Nusselt number is equal to 4.36. If you maintain the temperature of the wall as constant, then Nusselt number is equal to 3.66. Okay. Next one for turbulent flow, suppose if the surface temperature of the plate is higher than the fluid, then surface temperature of the tube is higher than the fluid temperature, then that case turbulent flow means Reynolds number value greater than 4000, then that is turbulent flow. If the surface temperature of the tube is higher than the fluid temperature or any liquid temperature, then Nusselt number formula is this one. Suppose ulta, then Ts is less than T infinitive, then this is the formula for that case. Okay, so that's all about the heat transfer correlations for laminar flow and turbulent flow in both cases, like flow over a plate, flow through the tubes. These things you just remember. We will solve a numerical problem based on this, then we will understand. Okay, thank you.